Hello everyone, welcome to the Makri Virtual. Hope you are doing good. Today I am going to continue with your same module, that is the procedural programming module, and with the same chapter, that is chapter number 19, that is interaction with the hardware, that is how to interact with the hardware. And in the yesterday's class, that was cancelled because I was suffering from fever in the last class, so I'm so sorry for the last class. And in the last to last class we have covered few topics, that is how to use the C programming, how to interact with the software, or how to interact with the hardware. So let's discuss the previous session what we have covered in the last class. In the last class we have talked with the hardware interaction, that is how to interact with the hardware using the DOS perspective. So it is using the DOS perspective, that is a disk operating system perspective, that is how to interact with the hardware. This says under DOS, whenever an external event occurs, if there is any external event, for example pressing a key, or using a timer, using the clock sense, using a motherboard, that's an external event. So whenever there is an external event occurs, or whenever there is an external event occurs, a signal known as the hardware interrupt get generated. So this is the DOS perspective. It is used for the external event and it is generating the hardware interrupt, and that is defined in the IVT table, that is the interrupt vector table that is used, that is looked up, or that is used for the different interaction, different hardware devices that is available. And IVT is always present in the memory, it is always available in the memory. Then we have discussed about ISR, that is the interrupt service provider that is used. Then this is the example. This is a diagrammatical representation that we have used. This is the key hit or the mouse click, that is either use the key hit or either use the mouse click. There is a microprocessor. Then after using the microprocessor, it looks up for the IVT, that is the interrupt vector table. Then it is using the address of the one ISR interrupt service routine, or either address of the interrupt service routine 2. Then a suitable ISR is called, that is suitable ISR is used. Then it is going for the either using the ISR1, either using the ISR2, that is the BIOS routine. So this is the diagrammatical representation how it will be used. So this says if we want that instead of the default ISR our routine should get called, then it is necessary to store the address of this routine in IVT. When this is done, whenever a hardware interrupt occurs, our routine address from the IVT is picked up and the control is transferred to the routine. So this is the diagrammatical explanation that we have discussed, that how to use the IVT and how we are using the IVT in the ISR. Then these are the 4 scenarios that we have discussed. These are the scenarios by which the explicit communication, by which the explicit interaction, that is the explicit means external communication, communication takes place between the C program and the hardware. So how this can be achieved? By using 4 methods, by using 4 activities. What are the 4 activities? One is the BIOS functions, one is the DOS functions, one is the library function, one is the using the direct interaction. So these are the 4 categories that is used, either by using the BIOS function, either by using the DOS functions, either by using the library functions, or either by using the direct interaction, right? So whenever it is using with the BIOS function, it is used either using the DOS functions, either using the library function that is used, right? Or either with the direct communication. So first one, our first category or first method is calling the DOS function that is used, that is either calling the DOS function. So to interact with the hardware, a program can call DOS function. So whenever there is an interaction, so there is a program that is called, that is calling the DOS functions. So that is one part, that is calling the DOS function that we have discussed. In this we have discussed that we have used BIOS, that is a basic input output system function that interacts with the hardware. As a result of this, the programmer is not required to know all the hardware details to be able to interact with it. However, since those functions do not have names, they have to be called through the mechanism of interrupt. So that can be done, or this is the default way how it will be used, how interrupt service number is used for using the different DOS functions. Moreover, communication with these functions has to be done using the CPU registers. That is, moreover, it is also used with the CPU registers. This leads to lots of difficulties since different function uses different register for communication. So one has to know details of different CPU registers, how to use them and which one to use when and why, etc. So these are the different scenarios in which we are using the CPU registers. Then second one is the calling BIOS function. So either the first category is the activities that is available with the external communication, either by calling the DOS functions. The next is either by calling the BIOS function, that is the basic input output function that is available under the C language. So these are the functions that is available, various tasks that is available like console input output, file input output, printing, etc. For other operations like generating graphics, carrying out serial communication, the program has to call another set of functions known as the ROM BIOS function. This is the next set of function that is available, that is known as the ROM BIOS function, that is used with the ROM BIOS that do the same job at the equivalent DOS functions do. It suffers from the same difficulties as the DOS functions suffer, as they do not have any names, or as they do not have any comparison operator that is used. Hence they have to be called using the interrupt and involve heavy usage of the register. So how they are used? They are used by using the interrupt, that is either software interrupt or hardware interrupt. The next activity that is used for the explicit communication or explicit communication is the using the library function. So one is using the DOS functions, one is using the BIOS functions, one is using the library functions. We can call library functions, which in turn can call other DOS and the BIOS functions to carry out the interaction with the hardware. So we can call the library functions which can be used, or which in turn can call the DOS and the BIOS functions to carry out the interaction with the hardware. Good examples of these functions, that is, what are the examples of the library functions like printf, scanf, that we are using in the day-to-day program also. That is how to use the scanf, how to use the printf, how to use the getch over here for interaction with the console, fsread, fswrite, and so on. So these are the various categories that is available. But the library does not have a parallel function for every DOS BIOS function. Hence at some point of time one has to learn how to call DOS BIOS function, that is how to use the DOS and the BIOS functions. Then the next one is using the, or there is a direct interaction with the hardware. So either we are using the DOS functions, either by using the BIOS functions, either using the library functions, or either directly interact with the hardware, or there is a direct interaction between the among the hardware or with the hardware. This is the most important point. However, direct interaction with the hardware is difficult because one has to have a good knowledge of the technical details of the chip that is using with the hardware. Then the next point that we have discussed in the last class is the hardware interaction on the basis of the Windows, that is the Windows perspective. So till now we have discussed the hardware interaction with the DOS perspective. Now hardware interaction with the Windows perspective. So this way is like DOS under Windows 2, hardware interrupt get generated whenever an external event occurs. As a reaction to this signal, a table known as the IDT, that is the interrupt descriptor table, is looked up and a corresponding routine for the interrupt gets called. Unlike DOS, the IDT contains the address of various kernel routines. That is, instead of using the BIOS routines. So it is using the same approach as the DOS programming, as the DOS perspective used, but the difference is that it is using the Windows perspective, or it is using the ISR, IVR, IDT that is used, that is the interrupt descriptor table. These routines are part of the Windows operating system itself. So when the kernel routine is called, it in turn calls the ISR that is present in the appropriate device driver. Now, two question arises or two question occurs. What are the two questions? Why the kernel routine does not interact with the hardware directly, or why the ISR of the device driver not registered directly in the IDT. So these are the two questions that arises, that why kernel does not have a power to directly communicate with the hardware, or why the ISR of the device driver is not registered directly in the IDT. What is the reason of why ISR is not registered directly with the IDT? That is the ISR and the IDT. Let us find out the answer of the first question. So we have find out the answer of the first question as well as the second question in the last class. This is the diagrammatical representation, how the hardware interact, or how there is a hardware interaction among the windows whenever there is a Windows approach, whenever there is a Windows perspective. So this is the diagram that shows if there is a key hit or if there is a mouse click, that generates an interrupt. So if there is any key hit or if there is any mouse click, that generates an interrupt that goes to the microprocessor. So if there is any interrupt, that first of all goes to the microprocessor over here. Then it looks up for the IDT. Then it looks up for the IDT, that is the using the ISR, that is the address. Then suitable routine is called, that is taken the routine like routine 1, routine 2, in the same way it is going, or it fetched from the ISR either by using the device driver. Then a suitable ISR is called. So if we are to gain fine control while reacting to the interrupt, we would be required to write a device driver containing a new ISR to do so. This says, under Windows, explicit communication with hardware is much different than the way it was done on the DOS. That is whenever we use the explicit communication with the hardware, it is much different than the way it was done under the DOS programming model. This is primarily because under Windows every device is shared among multiple applications. That is why, that is the reason it is the every Windows device, or under Windows every device is shared among the multiple applications that is running in the programming. To avoid conflict between different programs, that is there is a conflict whenever we use a different program simultaneously, Windows does not permit an application program to directly access any of the devices. Instead, it provides several API functions to find out the interaction. So for simple or for safer side, it is using the API function, that is application programming interface functions, for providing the various providing the interaction among the API functions. So to avoid the conflict, it uses the API functions to carry out the interaction. These functions have names, so calling them is much easier than calling DOS BIOS functions. So these API functions should have a name. So it is very much easier to call them either by using the DOS or the BIOS function. So this is the today's topic, that is how to resolve the conflict. So let's move to the today's topic. So we have covered the previous topic that we have discussed in the last class, because last class is not there or was not there. So for avoiding the conflict, it uses or it provides several API functions to carry out interaction. These functions have names, so calling them is very much easier than calling DOS BIOS functions. When we call an API function to interact with the device, it in turn accesses the device driver program. So whenever we uses an API function to interact with the device, to use with the device, it in turn accesses the device driver program. So that's look like a mediator, that is a device driver program for the device. It is a device driver program that finally accesses the device. So it is a mediator that is used to access the device for the hardware interaction with the device. There is a standard way in which an application can communicate with the device driver. It is a device driver responsibility to ensure that multiple requests coming from different applications are handled without causing any conflict. So for avoiding a conflict, we use the API functions. Under the API functions, there is a device driver who are able to handle multiple requests simultaneously, so there is no conflict among multiple applications. In the sections to follow, we will see how to communicate with the device driver that is able to interact with the hardware. That is how to use the device driver, or how device driver is able to interact with the hardware. One last question. Won't the API change if a new device comes into existence? That if there is a change in the API, if there is or the API changes if a new device comes into existence? No, it won't. This is the beauty of the Windows architecture. That is the beauty of the Windows architecture that used, it cannot access the Windows architecture. All that would change is the device driver program for the new device. So what is changed is the device driver program that is used with the new device. The API function that we would need to interact with the new device driver, that would remain same. This is shown in figure 19.4. This is the figure that shows how the device driver would remain, or how device driver would do the formatting, or how device driver would use the interact with the hardware with the help of the API functions. So first of all, there is a C program. Then after C program, there is a Windows API. That is an API function that is used. That is a Windows API. That is a Windows Application Programming Interface. Then there is a device driver. So C program interact with the API. Then API interact with the device driver. And in turn, device driver interact with the hardware. So in simple terms, device driver becomes a mediator between the API and the hardware, and the API becomes a mediator between the C program and the hardware. I'm repeating again. API provides an interface or becomes a mediator between the C program and the hardware, and the device driver becomes a mediator between the API and the hardware. So indirectly, the C program interact with the hardware. So hardware interaction is provided by the API and the device drivers. Now, communication with the storage devices. That is the next topic, that is how to communicate with the storage devices. This says, since DOS is commercially dead, the rest of the chapter would focus on communication with the devices under Windows platform. That is, DOS is not used in the day-to-day scenarios, so we will focus how communication is done with the under the Windows platform. We would illustrate this with the help of several programs. So let's start with the programs, let's start with the session, or let's start with this topic. So let us begin with the one that interact with the simplest storage device, namely the floppy disk. So let us start with the one, or let us begin with the one that interact with the simplest storage device, named as the floppy disk. Rather than the physical storage or physical structure of the floppy disk, it is the way the stored information is laid out and managed that concern programmer most. That is, we are using the floppy disk, that is the simplest storage that is used for the interaction. So rather than using the physical storage of the floppy disk, it is the way the stored information is laid out and managed that concern programmer mostly do. Let us understand how the information is laid out in a floppy disk. So let us understand the concept in detail, how communication is done, or how the floppy disk is able to store the data for the communication. Each floppy disk consists of 4 logical parts. So this is inside, or this is the structure of the floppy disk, that is divided into 4 logical parts. One is the boot sector, one is the FAT, that is the file allocation table, one is directory, and one is data space. So these are the 4 parts, that is the boot sector, FAT, directory, and the data space. Right. So these are the 4 parts, these are the logical 4 parts that is available in this. And then out of these, that is out of these 4 parts, the boot sector contains information about how the disk is organized. That is how the disk is organized, how this information is organized. That is how many sites does it contain. That is how many sites it will be organized, or how many sites it will contain for the organization purpose. How many tracks are there on each site. That is, first of all, it is divided into 4 parts. Then after dividing into 4 parts, out of the boot sector it is divided into tracks. Then after dividing into tracks, it is divided into sectors. That is, first of all tracks, then sectors. Then how many bytes are reserved for the sector. That means first of all there is a track, then there is a sector, then there is a byte that is reserved on the sector. And that is how many bytes are available per sector. The files and the directories are stored in a data space. So files and directories that is available are stored in a data space. The directory contains information about the files. That is, a folder contains the information, or folder contains the files like attribute, name, size, etc. The FAT contains the information about where the files and directories are stored in the disk space. That is, where the directories and the files are stored in the data space. Figure 19.45 shows the 4 logical parts of a 1.44 MB disk. That is, it is showing how it will be used. That is a 1.44 floppy disk that is used over here. This is the storage of the floppy disk. This is the diagram of the floppy disk. This is F1, 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 F1. This is F1, 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 F1. Then these are the F2, 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 F2. This is the base, that is the BS. In the same way, this is not a base. This is a boot sector. So it is given in the end. That is the boot sector. F1 means the first copy of the FAT. That is the file allocation table. Then second copy of the FAT. That is the file allocation table. Then D means the root directory structure, and the DS means data space. So as I told you, it is divided into 4 parts. One is the root directory, that is the directory. One is the FAT, one is the boot sector, one is the data space. So the floppy disk is divided into 4 parts as per this example, as per the scenario. So first part says there is a site 0, there is a track 0. The second diagram says there is a site 0, there is a track 1. So there are 2 sites that is available over here. BS means the boot sector, F2 means the second copy of the FAT, DS means the data space, and the F1 means the first copy of the FAT, and the D means the root directory structure. So these are available. One is the F1, 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 F2, then there is a boot sector, then D, DS, D. These are the various bytes, and these are the various bytes that is available, like 12, 13, 14, 15, 16. It starts with the 1, it ends with the 18. Here it starts with the 1, it ends with the 18. That means there are total 18 sectors on a floppy disk, and there are 2 tracks on the floppy disk. So 18 sectors and 2 tracks. So this is site 0, track 0. This is site 0, track 1. Right. Next paragraph says, with this logical, or with the logical structure of the floppy disk behind us, let us now write a program that would reach the floppy, that would reach the boot sector of a floppy disk and display its content on the screen. That is how it is able to display the content on the screen. But why on earth we would ever like to do this? Well, that's all. What's all Windows based antiviral software do when they scan for boot sector viruses? A good enough reason for us to add the capability to read a boot sector to our knowledge. Here is the program. This is the program that shows how this boot sector will be used. So these are the header files that is used. One is the stdafx.h. This is the hash include windows.h. Then hash include stdr.h. Hash include conio.h. This does the same, that contains the library functions like printf, scanf, This is the conio that contains the library functions like getch. This is the standard afx.h. This is the window.h that contains some predefined functions, library function that is available under the Windows. Then there is a hash pragma pack1, that is a hash pragma pack. This is also a pragma element that is available. Then struct boot. This is the struct boot that is available, that is defined a structure first of all, that is used for the boot sector, that is a struct boot. So what is the name of the structure? That is a boot. So we have defined the structure that contains the element. Now tell me, what is the structure? So structure is a data type that stores homogeneous data types, that stores the collection of not homogeneous, that is a heterogeneous data types. That is, one can define the int, one can define the float, one can define the char. That means any type of data type, any data type we are using, either char, int, float, anything. So that is a struct. So the name of the structure is boot, and the variable that is declared, one is the byte, that is byte, and the variable name is jump, that contains three elements, that is 0, 1, 2. So this is the array, that is name of the array is jump, and it contains three values, that is 0, 1 and 2. Then the next variable that is used, because it is char, it is struct, so we are declaring n number of data types. Next is your char, then bs own name 8. That is the array, again the array that contains 8 values, that is from 0 to 7. That is the bs om name that contains 8 values. Then word, that is word, that is a word. Then bytes per sector, that is also used. Then byte, that is byte. Then sector per cluster, that is used. Then word, that is also a macro, and the name of the variable is sectors, that is reserve. Then byte, then this is the copies fat, then word, then the max root directive, then word, that is total sector that is used. Then media descriptor, sector per fat, sector per track, then sides, then header sectors, and then char reserve, that is the 480 is used as an argument as an array, that is a char reserve 480. Then there is a closing of the struct, that is closing of the structure, that is a boot. The next the next function that is used is the read sector, that is a return type void, and these are the argument that is used. One is the char pointer src. So src is a pointer variable that has that is of type char, that is character. ss is of integer type. Num is of integer type. buff, that is buffer, is of void type, that is it is also a pointer that is of void type. Then there is a void main. So this is the structure declaration. Now this is the void main. Then uses struct boot b. So this is the variable of the structure that is used. The name of the struct is boot, and the variable that is used is b. Now there is a read sector, that is reading the sector. Then it is defined over here, that is a 0 1 ampersand b. Then there is a printf that is used, that is for printing in the line, that is the boot sector name. So it is displaying the name of the boot sector, that is the boot sector name, that is the b.id. Then byte per sector that is used, then b.bps. Then sectors per cluster, that is the b.spc. Rest of the statements can be written by referring figure 19.6 and appendix C. So this is the case, this is in written in the comment. That is rest of the program that is using, either you can refer the figure 19.6 or either you can use the appendix G that is available. This is printf as it is, that is for the read sector, so that we can read the content of the floppy disk, that is a printf, boot sector name, bytes per sector, sectors per cluster. Then the next one is void read sector, that is the next part, or that is the next element, that is the void read sector. Then these are the variable declarations like char pointer ss num buffer. This is the same as this one, so this is the function calling and this is the function definition. Then there is a handle, then there is a h, then unsigned int br, that is the unsigned int is used and the variable name is br. Then h equals to create file, then source, generic read, file share, read 0, open existing 0, 0. So this is used as this one. Then there is a set file pointer for setting the file pointer, for setting the values of file pointer, that is done by the set file pointer, and there are various arguments that is used. One is h, then ss into 512, then null, then file begin, that is the file begin is the beginning of the file. Then there is a read file, then h buffer, h buff 512 into num ampersand br, then there is a null. Then close handle, there is a h, that is a close handle function is used and there is a h. So these are used in a read sector, that is handle, unsigned int br, create file, set file pointer, read file, close handle h. Then there is a close handle for closing the files. This is handle that is for opening the file, that is for closing the file. The boot sector contains two parts. What are the two parts? That is the boot parameters and the disk bootstrap program. The boot parameters are useful while performing read or write operations on the disk. Figure 19.6 shows the breakup of the boot parameter for a floppy disk. There is a jump instruction. This is the jump instruction. The length is 3. The typical values is EB3 C90. Then OEM name, then 8, then MSWIN 4.1. Then bytes per sector, length is 2. Typical values are 512. Then sectors per cluster. These are sectors, number of FAT copies, maximum root directory entries, total sectors, media descriptor, sectors per FAT, sectors per track. There is a length, there is a typical values that is available, hidden sectors, huge sectors. So these are the various breakups that is used in this one. This is the explanation of this program, that is how it will used. So this is using the breakup of the bytes shown in figure 19.6. This is figure 19.6. Our program has created first of all structure that is known as boot. So the name of the structure is boot. Notice the usage of the pragma pact to ensure that the elements of the structure are aligned on a one byte boundary rather than the default 4 byte boundary. So it is used for the 1 byte boundary rather than the default that is used as the 4 byte boundary. Then comes the surprise, that is there is no win main in the program, that is there is no window main function in the program. This is because we want to display the boot sector content on the screen rather than in a window. That is, we want to display the boot sector that is available in the screen rather than in a window. This has been done only for the sake of simplicity. Remember that our aim is to interact with the floppy and not in drawing and painting in a window. That is, my target is for the showing the floppy disk, not to draw the images, not to draw the graphics, nothing. There is no interaction, there is no curiosity in this, but we have to simply read the or use the floppy disk in this one. If you wish, you can of course adapt this program to display the same content in a window. So the program is still a Windows application. Only difference is that it is built as a Win32 console application using VC++. A console application always begin with the main function rather than the Win main function. So a console application that is used is always begin with the main function rather than the Win main function. So it is used with the main function rather than the Win main function that is available over here. Right. So this is the explanation of the program, that is how to use the pragma, what is the Win main in this function. So this says there is no Win main in this program because it is based on the floppy. This is because we want to display the boot sector content on the screen rather than in a window. Remember, our aim is to interact with the floppy only, not to drawing the images. Our console application always begin with the main, that is whatever we are doing the program, that is a console application based program, that we have to begin the program with the main function rather than the Win main function. To actually read the content of a boot sector of a floppy disk, the program makes a call to the user defined function. So it makes a call to the user defined function that is known as the read sector function. This function is quite similar to the fsread library function that is available in Turbo C++ under DOS. That is a fsread function. The first parameter that is passed to the read sector is a string that indicates the storage device. So the first parameter that is used under the read sector function is the string that indicates the storage device from where the reading is done. The syntax for this is this one. So this is the first that is used, that is a machine name, then storage device name, then we have used this one for the machine name, and dot means that the same machine on which the program is executing. Needless to say, A refers to the floppy drive. The second parameter is a logical sector number. So this is the read sector. This is the read sector, this is the syntax, this is the name, then 0, then 1, then ampersand B. This is 1, then that occupies, or that means a single sector. The last parameter is the buffer that is reflected, or that is read from the floppy. Here we have passed the parameter of the ampersand B, that is the address of the boot structure, that is the B. As a result, the structure variable would be set up with the content of the boot sector data at the end of the function call. Once the contents of the boot sector has been read into the structure variable B, we have displayed the first few of them on the screen using printf. If you wished, you can print the rest of the content as well. Now, next is your read sector function. Right. This I will be starting in the next class. That is tomorrow's class. That is a Friday's class. Now I'm going to continue with the practical approach. That is how to do the practical approach with this one. So let's start with the practical approach right now. Or should I finish this one? No. Going to the practical approach. And now let's see how many pages are left. This is 649, 15 pages are left. So let's continue with this theory part only. Let's finish this function only, that is a read sector function, because this is very similar to the above function that we have discussed, that is a read function or the read sector function. This is the same function. So let's finish this one. So this says whenever we want to concentrate on the real program, we use the function that is known as the read sector function. This function begins by making a call to the create file. This function begins, this function starts with making a call to the function that is known as the create file function, that is the API function that is used like this one. This is the syntax of the create file function. This says h equals to create 5, then source, then generic read, then file share read, then 0, then open existing, then 0, 0. This says the create file API function is very versatile. So this is very versatile function. Anytime we are to communicate or we are to communicate with the device, we have to firstly call this. So whenever we have to use this or whenever we have to call this one or communicate with the device, first of all we have to use the function that is a create file function. So this function opens the specified device as a file, that is a create file. Windows treats all the devices just like files on the disk. Reading from this file means reading from the device. Then next one says create file API function that takes several parameters. That is the create file or create file API functions. The first parameter is the source, that is the src, that is the string that specifies the device to be opened. Then the second parameter is the set of flags that are used to specify the desired access to the file, that is a generic read, that is representing the device about the open. By specifying the generic read flag, this is the generic read flag, we have indicated that we just wish to read from the file, that is the generic read file, that is simply uses for reading from the file, reading from the device. Then the next one is file share read, that is used for sharing the resources across all the running application. Then we have to specify the file shared read, that means the file is shared among all the applications. In general, while interacting with any hardware, the sharing flag for the file, that is the sharing flag means the sharing flag or the sharing element that is used must always be set to this value, since every piece of hardware is shared among all the running applications. The fourth parameter, that is the 0, indicates the security access for the file. Since we are not concerned with the security over here, so we have specified the value as a 1. But if we want the security, we make it as a 1. The fifth parameter specified what action to take if the file already exists. That is, what is the action that is take if the file is already opened, that is the existing file. When using create file function for device access, we must specify the parameter as a open existing. Since the floppy disk file was already opened by the operating system a long time back during the booting, the remaining two parameters are not used when using create file API function for device access. Hence, we have passed a value 0 for them. That means there is no API function for the device access. If the call to the create file succeeds, then we obtain a handle to the file. So in simple terms, this is the explanation of this one, that is a source, that is a generic read, this is also a flag, then the file sharing among the applications, then 0, then open existing, then 0, 0. The device file mechanism allows us to read from the file by setting a file pointer. So this is the file pointer that is also used, that is the set file pointer API function, then reads the file using the read file function. So two functions are used. One is the set file pointer function, and for reading purpose it uses the function that is a read file API function. Since every sector is 512 bytes long, since every sector that is available is of this much long, to read from the nth sector we need to set the file pointer to the 512 into n bytes from the starting of the file. The first parameter to this one is the handle of the device file that we obtained by calling the create file function. That is the first parameter that is used is the handle of the device that we are obtained by calling the create file function. The second parameter is the byte of offset from where the reading is to be begin. This second parameter is relative to the third parameter. We have specified the third parameter as a file begin. That is the third parameter that is used, which means that the byte offset is relative to the starting of the file. The next paragraph says, to actually read from the device file, we have made a call to the read file API function. So this is the function that is used This function is very easy to use. That is a read file function. The first parameter is the handle of the file. That is, first parameter is the handle of that file, that is device that is used, and the second parameter is the address of a buffer where the read content should be dumped. That is where read content should be followed. The third parameter is the count of bytes that have to be read. We have specifies the values as a 512 into num so as to read num sectors. The fourth parameter to read file is the address of an unsigned int variable which is set up with the count of the bytes that the function was successfully able to read. That is the counting of the file. Lastly, once our work with the device is over, we should close the file by using the close handle function. So this is the read handle, read file function is used, that is used to read the file, that is used to take the or count the number of bytes. Then at last it is close the file or it is close the device, that is done by the close handle API function. Though read sector does not need it, there does not exist or there does exist a counterpart of the read file function. Its name is write file, that is the for writing purpose. This is used to write to the file. So one is for the reading the file, one is for writing the file, one is for closing the file. This says the write file is to be used when we need to specify the generic read. So generic read flag is used for whenever we call the function, that is the create file function. Given below is the code of the write sector function that works exactly opposite to the read sector function. Then this is the void write sector. These are the various argument that is used, that is char, pointer ss, int ss, int num, void pointer, buffer. And these are the various variables that is used. That is the handle is the macro h, unsigned int br, then h equals to create file, src, generic write, file share, write 0, open existing, 0 0. Then there is a set file pointer, then h, ss into 512, null, file begin. Then there is a write file h, buffer 512, br, null. Then there is a close handle, that is for closing a file. Then there is a h. Then this will be closed. Now the next topic is accessing the other storage devices. That is how to access the other storage devices. That is the next topic. That is how to use with the keyboard, how to communicate with the keyboard. This says, note that the mechanism of reading from or writing to any device remains standard under the Windows. That is, a mechanism for reading any file or from reading and writing from any device is a standard form that is available in the Linux. That is a standard one. We simply need to change the string. That is, everything is same, but simply change the name of the string whenever we want to use other device other than the floppy disk. Right. Here are some sample calls for reading and writing from or to various devices. First of all, there is a read sector. Then again, there are various arguments that is used, that is reading from second floppy drive. Then again read sector. Then again this is the argument that is reading from CD-ROM drive. Then write sector. Again this is the argument. Then writing to a hard disk. Then again read sector. This is the argument. Then reading the partition table. So these are the various tables. These are the various 4 parts that is used. One is for read sector, write sector, read sector. Here are few interesting points that you must note. Now, the first point is, if we are to read from a second floppy drive, then we should replace A with B while calling the read sector function. That is, whenever we want to read from the second floppy drive, second floppy disk, then we should replace A with the B. That is done by this one while calling the read sector function. To read from the storage devices like hard disk drive or CD-ROM or zip drive, we use the string with the appropriate letter like this one. These are the various devices, these are the various parts that how to use the various devices that is available over here. Then to read from the CD-ROM, just specify the drive letter of the drive. Then next point says the hard disk is often divided into multiple partitions, that is C drive, E drive, F drive. These are the various partitions. The next point says using this absolute path we can also read the content of any other parts of the disk. Here 0 represents the first hard disk in the system. If we are to read from the second hard disk, then we need to use 1 in place of the 0. Now next topic is communication with the keyboard. Then that I am going to start in the next class, that is how to do the communication with the keyboard. So that's all for today's session for the theory part. Now let's move to the practical part. So now let's move to the practical part. In the last class we have studied about the arrays, that is how to pass the string, how to reverse the string, how to use various functions. So this is the last class topics. Now today I'm going to write a program to print the elements or to print the array or two-dimensional array, right? So remember what is a two-dimensional array? That is in the form of rows and columns. So this is write a program to display the elements of 2D array. Right. So there are first of all header file that is used, that is hash include stdio.h, then hash include conio.h. Then there is a void main function. Then there is a variable declared, that is a int I comma j. These are the two pet a variable that is declared whenever we use the matrix, whenever we use the 2D array. Then uses int a. Now define the array like this one, that is 3. This is the rows, then this is the columns. That means 3 rows and 3 columns are available. Then uses the curly braces, then uses the bracket, that is 1 2 3 for example. Then in the second one this is 4 5 6, then 7 8 9, then closes this one. That means there are 3 rows, 3 columns, and these are the 9 values that is available in the array. Now clear the screen. Now simply uses the printf, that is printf elements of the arrays are that is elements of array. This is printed here. That is also using by using the next line, that is /n/n. That is, there is a gap of the 2 lines. Then this is the also the pet for loop that is used in each and every 2D array. So it starts with the I, that is used for the rows, that is I equals to 0, then I is less than equals to 3 or less than 3, not equals to because it is array, 3, then I plus plus, then again this is 4, this is like this one, 4, that is j equals to 0, j is less than 3, then j plus plus, then again this one, that it start with 0 ending with j, then j plus plus, then simply printf uses the percentage d over here, then a I j, then simply prints to the next line, that is printf, that is slash n, then for loop, then moves to the next part, uses the get ch only, so that the output will be printed over here, that is the get ch, then simply closes this one. Now if I compile this code, there is one error, declaration syntax error. There is no semicolon at the end, that's why it is declaration syntax error. Now if I compile, there is no error. If I execute this program, this will print like 369000, so there is some error, or there is some error in this one. That is percentage d ai j, j equals to 0, j is less than 3, j plus plus. There is a void main ij a33 123. Alright, this is not brackets, this is also a curly braces. Now if I compile this code, there is a success. If I execute this code, yeah, this will be printed, that is 1 2 3 4 5 6 7 8 9. But what is 0 3 0 0 0 4? What happened? That is elements of an array. This one. If I again compile this code, that is elements of an array is this one, that is aij percentage d. Some garbage value is also arrived over here, that is for printf. One for loop is used, then this is the closing of this one. Now if I compile this code, there is success. If I execute this code, this is printed 1 2 3 4 5 6 7 8 9. Then there is 0 3 4 4 0, that is not correct. Now let's see. Everything is same, but the crux is that the last output is not coming correct. Equal to 0, j equals to 0, j is okay. Here I have written in by mistaken, j is equal to 3. Now this is correct. Elements of the array are 1 2 3 4 5 6 7 8 9. That is, array is printed in a sequence. Now if I want to give a tab between this one, that is, there is a tab in between these spaces, so there is a tab. Now if I compile this code, this will print in a tab form, like 1 2 3 4 5 6 7 8 9, in a row format, in a matrix format, in a 2D array format. So now let's see what is the program, what is the uses of the program, and how we are able to do this program, or how we are able to write this program. So first of all, there are two header files, that is the hash include stdio.h, that is the header file, then hash include conio.h. Then there is a void main, that is a starting function. Then there is a variable declaration like int ij. Then there is a int a33, that means the array is declared of the a, the array name is a, and there are two parts, one is rows, one is the columns, that is a 3 3. Then 1 2 3 4 5 6 7 8 9. So these are the three parts that is available, That means the array is declared over here. That means 3 rows and 3 columns. So there are total 9 values, that is 1 2 3, then 4 5 6, then 7 8 9. Then there is a clear screen, that is a CLR SCR. Then there is a printf, it is printed as it is, that is the elements of the array, that is the elements of array. Then using the for loop, that is I equals to 0, I is less than 3. That means it starts with the 0, it ends with the 2. So it runs for the 3 times, 0 1 2. So it starts with 0, then end with the 2. Then again there is a for loop. So one outer loop is for the rows and inner loop is for the columns. Inside the inner loop, there is a printf statement, that is a aij. That means every time it will increment and every time it will print. Then for moving to the next line, after the curly braces, it is given printf/n, that is also available. Then there is a getch statement for the printer or for the output purpose. So first of all, there is a now let's try run the program. First of all, it is using I equals to 0. That means first of all, the value of its starting point is I equals to 0. Then I is less than 3. It checks the condition. Condition is true. That is 0 is less than 3. The condition is true. Then moves to the inner loop. Now, first of all, the inner loop will execute. Then only moves to the outer loop. So the inner loop is j equals to 0. J is less than 3. Condition is again true. Then moves to the inner side, then print aij. Now I has a value 0, j has a value 0, so prints the output at the 0 0 location. 0 0 location means the first location, that is the 0 0 location, right? Then simply moves to the next line, that is a printf/n. Then gets ch for the printing purpose. Then again moves to the next one. That means first of all the 1 will be printed, that is at the 0 0 location this 1 will be printed. Now after using this curly braces, again moves to this one. Now j becomes 1. 1 is less than 3, condition is true, but I becomes, or I is still 0. So this is 0 and 1. So at the 0 and 1 location it is printed as a 2. Again moves to this one. Now the j becomes 2. 2 is less than 3, condition is true. Then it uses aij, that means 0 and 2. At the 0 2 location it is printed as a 3. Then again it becomes 3. 3 is less than 3, condition is not true. Then it will terminate and moves to the next line by using this printf. Then there is a /n. Then uses this one, again moves to this one. Now I becomes 1. Why? Because first of all it is 0. Now there is a I plus plus, so it becomes 1. Check the conditions. 1 is less than 3. Condition is true. Why? Because 1 is smaller than the 3. Then moves to this one. Now j is 0 because this is the starting phase. So check the condition. Sorry, j is 0. Yes. Check the condition. 0 is less than 3. Condition is true. Moves to the inner side. So this is 1 and this is 0. So at the 1 0 location it is printed as a 4. Right. Again moves to this one only, not moves to this one. Why? Because this is not terminated yet. So first of all the inner loop will terminate, then only moves to the outer loop. Right. So this is 1 is less than 3, condition is true, so it will print at the 1 1 location 5. In the same way 1 2 location 6. Then moves to this one, the condition is false, again moves to this one. Now I becomes 2. 2 is less than 3, condition is true, moves to inner loop, j equals to 0, j is less than 3, j plus plus, then ij. So I has a value 2, j has a value 0. So at the 0 2 location it will print 7, at the 2 1 location it will print 8, at the 2 2 location it will print 9. So these 9 values will print like this one. First of all in the first row, then second row, then in the third row. This is the program that shows how we are able to print the 2D matrix, that is a 2-dimension matrix. Right. So this is the program for the 2D array. This is the output of this program, that is 1 2 3 4 5 6 7 8 9. If I want that there is some little bit space between this one, there is no space of the gap, so there is I'm giving 5. There is little bit space, 1 2 3 4 5 6 7 8 9. There is no gap of the tab, but there is a gap of the 5 pixels. If I want to convert into 2, there is a small gap, like 1 2 3 4 5 6 7 8 9. So this will print like this one. So that means we are giving 2. That means there is a 2 margins among each and individual numbers, each and individual elements of the array. This is the way how we are able to print the 2D array. But this is the program of the predefined. That is, we have already defined the values in the above part. Then we are able to use this. But we are also using whenever we are able to get the input from the user. That is, we are not defining the value, but we are able to get the input from the user. Right. Now, first of all, I save this one. That is array. This is, first of all, it is done, or it has already made. Then this is the array. Now if I change this one to 2 2, let's say example. Now what is the output? There are 4 errors, too many initializations. That is, there are too many initializations. That means if the value given is less, but if the index given is less, but we are giving more than one value, more than that value, that is also an error. So this must be 3 3. Now if I change to this one as a 2, again 2, what is the error? The 2 value that is printed, that is a 1 2 4 5. That means it will not go for this one, not go to this one, not go to this one. It will print only 2 values. So this is the outer loop, inner loop. This is the outer loop. First of all, inner loop will execute, then only moves to the next one. Now if I don't give this one, now let's see what is the output. This will print only in the one line, that is 1 2 3 4 5 6 7 8 9. That means there is no line gap. If I want the line gap, then simply use the printf /n. Right. There is one error, expression syntax. That is, there is expression syntax. Now if I again compile, this is 1 2 3 4 5 6 7 8 9. Now if I change these values, this is, for example, 11, this is 30, this is 24, this is 52, this is 65, this remains 7, this is 84, this is 09, for example. Right. If I compile this code, there is one error, illegal octet number. That is, we cannot give the values over here. It is 95. So that will print the numbers like 11 13 0. This is the number. No, 1 11 13. So this is 1 11 13 24 52 65 7 84 95. So this is not a proper sequence. Now if I give exactly in a 2 2 format like this one. Now if I execute this, this is in a proper sequence. So I want a more gap. So here I have to write 90. Now if I compile this code, there is a proper gap in between the Awesome. This program is clear to you? And what about Larry? This program is clear to you, everyone? Hello? Okay. So I'm finishing this class over here only, and in the tomorrow's class I will be starting your next topic, that is communication with the keyboard. That is how to communicate with the keyboard. Today we are able to study, we have studied that how to communicate with the storage devices. Now the next part is how to communicate with the keyboard. So that's all for today's session. Thank you so much. If you have any doubts, then please text the doubt and I will answer you. Alright, so everyone, bye bye. Yes. Yeah, Larry, tell me. Pa- VC++. Yes, yes, yes. What type of error? So just do one thing. Take a snapshot of the errors and mail to me. Okay, then I will see what is the error. Okay, all right. Bye bye.